Hey guys, here with a bonus video for y'all, just in case you are interested in the last of the applications for L'Hopital's rule. There were a bunch of exponential forms, indeterminate forms that we mentioned, were things that we can't immediately evaluate just by looking at them. Now, if you're in my morning class, we flew through an example at the end. If you're in my afternoon class, we didn't quite make it to one of these examples. So, just so you guys have seen it, I wanted to figure that we can go ahead and take a little bit more time taking a look at a couple of these examples more carefully, just so you guys see how we can handle all of the indeterminate forms using L'Hopital's. Okay, so to get started, first off, L'Hopital's rule says we can fix these indeterminate forms 0 over 0 or infinity over infinity. Cool, that's great, but those exponential forms that I listed, 0 to the 0, infinity to the 0, 1 to the infinity, pretty much none of those guys look like a fractional indeterminate form, so we can't immediately work with those using L'Hopital's rule. However, that doesn't mean that we're totally, stuck in the mud here. There's a trick that we can use to apply L'Hopital's rule to one of those forms that looks like some function f raised to some function g. And here's what that trick is. What we are going to do is abuse some inverse functions, right? We'll start out with, if I can get my pen to work here, we'll start out with f to the g being equal to e to the natural log of f to the g. Reason we can do this is the exponential and natural log functions are inverses of each other. So, e to the log of whatever, this would cancel and give me f to the g. But we're trying to do a rewrite here, so it's okay that it temporarily looks more complicated. Next thing that I'll do in my rewrite is I will go ahead and apply my natural log rules and bring down this g that was in the exponent of f as a coefficient on my log term. Right, so I no longer have an exponent up there. Now, a comment about what's going on here. This bit right here should, in general, look like basically a 0 times infinity or infinity times 0 form. Okay, or alternatively, if we're super lucky, we can rewrite this pretty directly as a 0 over 0 or infinity over infinity form. Now, the way that this is going to differ from some of our previous examples is, rather than applying L'Hopital's to some sort of overall fraction that our limit gets rewritten to, you notice this has this pesky exponential here. What I'm going to do is pass my limit through this continuous function so I can apply L'Hopital's rule just on the exponent. So at this point, what I'm looking to do is just do L'Hopital's on this exponent term. Okay, so I'll go ahead and give you guys an example. Let's go ahead and start here with, if you're in my morning class, you've seen this before, but we'll do this a little bit more carefully this time. I want the limit as x goes to infinity of x to the 1 over x. If I am concerned with what form this is of, well, it looks like infinity raised to the 0. If we went back to that previous page, you'll notice that this is one of those forms. So we can apply our tricks. First thing that you'll notice I can do is, we said we wanted to take e to the natural log of whatever our f to the g limit was. Right? So here, what's that going to look like? This will look like x to the 1 over x here. And once I've taken that, I can apply my natural log rules. Right? My natural log rules say that I can bring down exponents as coefficients. So this will look like 1 over x times natural log of x up here. Now, as a side note, if I'm just focusing on this exponential term up top, that part right there looks a lot like a 0 times an infinity limit. Now, there is a pretty quick and easy rewrite to this if I wanted to, just multiply straight across with that fraction. What this is going to turn into is then e to the natural log of x over x, right? So that part there, if I'm just looking at that exponential term, this now looks like infinity over infinity, which would be great for me to apply L'Hopital's rule to. Now, for those of you guys that are maybe a little bit fishy on, well, the fraction's not the whole function, why can I just apply it to the exponent? There is a tiny little theorem that we mentioned a long time ago in the continuous functions section that allowed us to pass pass limits through continuous functions. The main application of this that we've seen thus far is it extended the reach of the direct substitution property, right? We could prove with the algebraic limit laws that polynomials and rational functions, if you can plug it in, go for it. But this let us do that for things like cosine and sine and exponentials and logs, and we're going to use the same property here. Basically, what it lets us do is take this limit and pass it through the continuous function e to the x. So what this will look like is now e to the, whatever the heck this limit comes out to, right? The limit of this upper exponent function here. This is technically why we're allowed to use L'Hopital's rule just in the exponent and ignore the e. Now, at this point, I'll scroll down and give myself a little bit more room. If I wanted to apply L'Hopital's rule to that exponent, since we do have an infinity over infinity form, I'm basically taking the limit out at infinity of what happens when I derive the top, get 1 over x, over what happens when I derive the bottom, I get 1. Well, there's no real point in dividing by 1. This is going to look exactly the same as if I'm just taking a limit of 1 over x, but, here I can actually take that limit, right? We've got a increasing denominator, that fraction is going to shrink. This will look like e to the 0, which most regular numbers, like e, if I take them to the 0, they are determinant forms. Okay, this isn't 0 to the 0 or infinity to the 0, so we're in the clear. Okay, anything that's not one of those, raise it to the 0, and we're just going to get 1 back. Okay, now, just so that you guys have seen a little bit more complicated of an example, let me try one more before I run off here. We will try, and this is a really famous limit in mathematics. You'll hopefully see when we get to the result why. The limit as x goes to infinity of 1 plus 1 over x raised to the x. If you've seen this at all before, usually the way that this is expressed is in terms of n's instead. Limit as n goes to infinity, 1 plus 1 over n to the n. At any rate, the variable's not important. The value that you get back either way will still be the same. And you'll notice that this form here, if I actually tried to, substitute in infinity as best as I can, this fraction up here, the 1 over x, that shrinks off to 0. So this really just looks like a 1 to the infinity form, which is an indeterminate form here. So we had to apply our method, right? That's going to involve first starting off by taking e to the natural log of whatever expression we were starting with in the first place. And once you do that, your next step is going to be to bring down whatever power that you have as a coefficient on your natural log term. Okay, so that will look like so. Now, you'll notice if I'm looking at forms of this exponent up top, let's be careful to make note of what we have. If I'm taking a limit as x goes to infinity, the x itself is obviously going to go to infinity. This log term, though, you'll notice that if I try to substitute infinity in for x, the fractional bit will shrink, so that I'm ultimately taking natural log of 1. And what does natural log of 1 evaluate to? It goes to 0. So we've got an infinity times 0 expression. Now, recall, the way that we handle these is we're going to flip okay, one of those terms. We said that if you have f times g, this is either going to go to f over 1 over g, or it'll turn into g over 1 over f. Now, in this particular case, which one of these guys do we want to flip? Now, I've mentioned before that usually it's a bad idea for us to try to flip these polynomial terms, because then you get negative powers in your denominator. Those negative powers usually don't ever go away, but let's just write out both options for sake of comparison here. Okay, so just for sake of comparison, I'll just do this in scratch work in red. We've got one of two options, right? If I take my f over 1 over g versus if I take my g over 1 over f, these are the things that we're going to get. If I keep f, that means I'm keeping my x, and I'm trying to flip my natural log term. Okay, on the other hand, if I keep my natural log term, then what I'm going to flip is my x. So I'll get a 1 over x. Now, some of the examples that we've done in class for this infinity times 0 thing, these flipped expressions can simplify a little bit. In this particular case, there's not much simplifying that you can do to natural log. So while the top derives very nicely here, this will turn into a 1, and it'll disappear very quickly. You won't be able to L'Hopital that again. This bottom, though, you have basically got chain rule within chain rule within chain rule. Or potentially, if you want to avoid chain rule, you've got quotient rule, which is possibly even nastier, right? You know, I can view this as natural log of 1 plus 1 over x, that whole quantity raised to the 1, and that's going to have a disgusting derivative. Here, I've got chain rule, okay, but it's just one pass of chain rule, not two. And actually, the insides look a little bit similar, right? If we think about this kind of hard, when I apply chain rule, I have to multiply by the derivative of the inside, and you know, that same derivative is going to pop up when I take the derivative of the bottom. So maybe in this one particular case, this is looking like the nicer option to go with. So let's try that one in our rewrite. Okay, I'll switch back to my ink color here, my standard ink color, when I do this rewrite, since we've nailed down a selection to use. I am now rewriting this as e raised to this bit in the red here. Natural log of 1 plus 1 over x divided by 1 over x. And I will scroll down to give myself a little bit more room. The thing that I'll notice about this particular form is up top, well, what this looks a lot like is, if I try to think about plugging in infinity, I've basically got a 0 over 0 form up top here that I can apply L'Hopital's rule to. So this e, we can worry about him later. The hard part of this problem is really going to be worrying about what happens with this fraction that I've built myself by flipping terms. Okay, I will go ahead and apply L'Hopital's rule to that function. Here, if I do that, I will need chain rule up top. Your derivative of the natural log function is 1 over the inside of the log multiplied by the derivative of the inside, which the 1 drops off, and we're deriving x to the negative 1. So that'll be negative x to the negative 2. I still have to go back and derive my bottom function, which is effectively x to the negative 1. Well, power rule says that will be negative x to the negative 2. Whenever you're doing L'Hopital's rule, you want to simplify as much as you can to evaluate. So at this point, we are left with worrying about what the limit of 1 over 1 plus 1 over x is. You know, that's a lot of 1 overs, but if I'm thinking about what this limit is doing, you know, x is blowing up, this 1 over x fraction is going to shrink off to 0, that means we're really just left with this 1 over 1, right? I have got a limit of e to the 1 over 1. That simplifies to e to the 1, and the reason that I have mentioned that this is a famous limit in mathematics is because this is one of the standard ways that we get to derive the constant e. If anybody has any questions, please feel free to let me know.